So we were aiming for the longest and most technical title in the whole conference, and I think we succeeded. So this is a talk that's going to be about influence in completely bounded block multilinear forms. I'll tell you what it is, and then their consequences in terms of classical simulation of quantum algorithms. And this is joint work with Nikhil, Bansal, and Makrand, Sinha. So what is the motivation here? The motivation is comparing classical and quantum query complexities. So the setup is that we run an algorithm. The algorithm has an n-bit input. And the way we access the bits of the input is by making queries. So we are allowed to, does this work? We are allowed to, let's say in the quantum case, use unitaries of this form that would map I, 0 to I, xi. We can also use phase queries. In the classical world, you can just think of this as some sort of box. You put in a number I, out comes the bit xi, and this is how we access the bits of the n bits of our input. And the complexity measure is the number of queries we make in our algorithm that's supposed to compute f at the point x. So the question is, how many queries are needed by the best algorithm to compute some particular Boolean function f that we're interested in? So this is a function that maps n bits to 1 bit. Let's say with worst case error probability 1/3, right? And we're going to compare quantum algorithms that achieve this with classical algorithms that achieve this, and our complexity will be measured by the number of queries. This is sort of like an information theoretic measure of complexity. And it's known that if f is a total function, and that means that it's defined on every possible n-bit input string, then classical and quantum query complexity are not too far apart. So we had this paper 25 years ago that showed that these two complexity measures are at most a power of 6 apart, and this was then improved maybe 5 years ago by Aronson et al. To a power of 4. In any case, if your function is total, you can't really expect very much speed up in terms of query complexity. Situation is totally different if you have a promise on your input. So if not every possible input n-bit string is allowed as input, but somehow there's some sort of promise that your n-bit string will satisfy a certain nice property. So there are partial functions on sort of subsets of the n-bit Boolean cube where we can get exponential separations, right? So you can formulate Simon's problem in this form. Shor's period finding problem is of this form. These are kind of partial functions on inputs satisfying nice structures. For instance, periodicity in the case of Shor's algorithm. You can even have unbounded, like sort of constant quantum queries versus almost linear classical query separation for problems that are called K correlation. Think of K as a constant here. And so what this shows is that if you want to get large superpolynomial quantum speedups, you're going to need some structure on your input. You should sort of act on, you should restrict your input x to come from some structured set, and only then can you hope for superpolynomial speedup. And then you can ask the question, and this has repeatedly been raised by Scott Aronson and others, like how much structure is necessary to get significant quantum speedups in query complexity, right? So you can think of more structure corresponding to a smaller promise set D. Like the more structure you impose, the smaller the set of D of allowed inputs is, right? And so qualitatively, the question is how much structure is needed for large quantum speedups. And Aronson and Ambainis, they formulated an interesting connection with analysis of Boolean functions. Namely, they showed that that large influences in your function, like if they're variables with large influence, they will actually lead to efficient classical simulation of quantum algorithms on almost all possible inputs. And the connection goes through polynomials. So we developed this polynomial method for quantum algorithms, and sort of the core statement is that if you have a T-query quantum algorithm on your n-bit input, then its acceptance probability, so its probability to output a 1, can be written as a multivariate, n-variate polynomial that takes an n-bit input, maps it to a number between 0 and 1. Would be the acceptance probability on that particular input. And the crucial point is that this polynomial will have low degree. If you had an efficient algorithm, so if the number of queries is small, then your polynomial is going to have low degree. Its degree will be at most twice the number of queries. And just a little bit of technicality. So if you have such a polynomial, so a bounded polynomial on the Boolean cube, you can define its variance in the usual way. So the polynomial has an expectation, and you can look at the expected squared difference with respect to the expectation, where the expectation is taken uniformly over the set of all possible n-bit inputs. And similarly, you can define the influence of a variable I, xi, on such a polynomial as follows. So this is, forget about this factor of 2 here, that's just there for technical reasons. Effectively, what this is saying is that the influence of variable I on the polynomial p is big if on many inputs, flipping the ith variable leads to a big change in your polynomial p. And both of these expressions have very nice sort of reformulations in terms of the Fourier coefficients of the polynomial p. I won't really write that on the slide here, but these are very convenient expressions to work with. And then the Aronson-Abinas conjecture says the following. It says that every degree d polynomial of this form has a variable of fairly large influence. So if the polynomial has significant variance, let's say at least a constant, and it has somewhat low degree, then there must be a variable I, xi, such that the influence of that variable is at least some polynomial in the variance on 1 over d. And this is a sort of a tough to prove conjecture. A lot of the best people in classical analysis of Boolean functions have sort of cracked their head against the wall trying to prove this. We don't know if this thing is true. Like the gist of my talk is a proof of a special case of this. But the nice thing about the Aronson-Abinas conjecture, and this is the connection with quantum algorithms, is that if it is true, you can take a quantum algorithm and you can simulate it almost everywhere on almost all inputs very efficiently, with at most a polynomial blow up in the number of queries. If you go from, so you go from T quantum queries to polynomial in T classical queries, and you would sort of be simulating your quantum algorithm on almost every point in the Boolean cube. And here's the algorithm. It's sort of the obvious thing, right? So suppose you have some quantum algorithm. Its acceptance probability is some polynomial p of that form of low degree. Aronson-Abinas conjecture, if it's true, would guarantee you that at least one variable has significant influence there. So what is your classical algorithm going to do? It's just going to query that bit. And you can show that on expectation, this will reduce the variance of your polynomial a little bit. And now you recurse, right? So you query xi, let's say I is the influential variable. You plug in whatever you got back. You get a new polynomial on n-1 bits. You again apply Aronson-Abinas, and again there will be an influential variable in this new polynomial. You query that one, and you keep going. And every step, because you are querying influential variables, the variance of the remaining function is going to drop in expectation. So you keep doing this until the variance is very small, let's say much smaller than epsilon squared or something like that. And at that point you're almost done, because if you have a polynomial with very small variance, that means that on almost all possible inputs it is actually close to its expectation. Right? If you have a variance bound, you can use something like Chebyshev's inequality. So what is your classical simulation going to do now once the variance has dropped to something small? It's just going to output the expectation. Right? So this is the algorithm that you sort of the classical simulating algorithm that you get. It's quite easy if the Aronson-Abinas conjecture is true. And here's the relation to the how much structure is necessary for speed up question that I asked in the beginning. So suppose you have a T-query quantum algorithm for some promise function, so where the domain D is some subset of the Boolean cube. Let's say that the subset is not too small. Then what this conjecture, what this sort of simulation is saying is that your quantum algorithm for this promise function can be simulated almost everywhere with small blow up. So you get a classical simulation, which is not much worse than your classical, like it's slightly slower in terms of queries than your quantum algorithm, and it's good. In fact, not only on almost all the points of the Boolean cube, but almost all of the points within your promise. Right? That's because if the promise is fairly large, let's say 1%, and you simulate it correctly except for 0.1% of the Boolean cube, you're actually doing well even on sort of almost all of this promise set. Right, so this is the connection with quantum algorithms. And what we're going to do in the rest of this talk, it's purely a math talk, the rest of this talk, is prove a special case of the Aronson-Abinas conjecture. So for polynomials P that have some extra properties. So what is our result? Like I said, our result is a special case of the Aronson-Abinas conjecture. And it is for polynomials of this form. And so this is going to be slightly technical. So the number of input bits is now actually, they're going to be divided into D separate blocks, each of little n bits. So the total number of input bits, I now call it capital N. So the total number of capital N input bits is divided into D blocks of little n bits each. And the monomials in your polynomial, they have the nice property that each monomial here contains at most one variable from each of the blocks. Right, so these things have degree at most D, because there's D blocks. They could have less than D. You're not required to In a non-homogeneous case, you're not required to have monomials of degree exactly d here. So this is the Block-multilinear aspect. And then in addition, we want the property that this polynomial p has a so-called completely bounded norm that's at most 1. Right, and like all this stuff together sort of explains most of my title. Let me just tell you what this completely bounded norm is. It's kind of nice. It also connects to quantum algorithms in a way that I'll mention in a moment. So the completely bounded norm is the following. So you're thinking of this polynomial now not as a function on bits, pluses and minuses, but as a function on unitaries. So each of these capital N variables, you can actually substitute a large dimensional unitary for it. Right? And if you view it that way, then this polynomial, this is like a non-commutative polynomial because different unitaries need not commute. And then what you do is, so you stick in a large dimensional unitary for each of the variables. This gives you a new matrix. This matrix will have an operator norm. And the CB norm is defined as the biggest operator norm you can get in that way. You're implicitly also maximizing here over the dimension d. Think of d as very, very large. So it's like you're plugging in very large dimensional unitaries for these variables, and you're trying to maximize the operator norm of the resulting matrix. Right? And then the assumption on this thing here is that the completely bounded norm of this polynomial p is at most 1. And this looks like a super special case, like embarrassingly small special case of the Aronson-Ambinus conjecture. But it is actually sort of very closely related to quantum algorithms, generic quantum algorithms in the following way. In fact, every T-query quantum algorithm on little n bits, there will exist a completely sort of Block-multilinear, completely bounded polynomial on capital N bits, where if you were to substitute the same little n bit string for each of the d blocks, you get the acceptance probability of your quantum algorithm. So structurally, this is actually pretty close to what arbitrary quantum algorithms can achieve in terms of polynomials. Nevertheless, a proof of the Aronson-Ambinus conjecture for this special case, which is what I will give in the rest of the talk, does not imply a general proof of Aronson-Ambinus, because the existence of a sort of high influence variable here does not imply the existence of a high influence variable here. Right? Because this little p here, this sort of looks at a tiny, tiny corner of the capital N-dimensional Boolean cube. Okay, so I think this is going some way in the right direction, but it's definitely not a proof of the general Aronson-Ambinus conjecture. And what I want to do now is just give a proof sketch for the special case where p is of this form. It's degree d, it's Block-multilinear, and its completely bounded norm is at most 1. Okay, so let me first give you a failed attempt, which is still sort of instructive. And that is the following. So let's start with a special case where our polynomial is actually homogeneous. And homogeneous would mean that each of these monomials contain exactly one variable from each of the d blocks. So all of the monomials have degree exactly d. Right? That's even more of a special case, but that will turn out to generalize later. Now, if you have a homogeneous case, then you can sort of pull out the very first variable, like you can pull out the variables of the first block. Right? So this superscript here, this refers to the first block of little n variables. And I'm summing over these variables, and here I'm collecting all the monomials that contain this particular variable. Right, this is just simple rewriting. And then this thing I'm going to give a name. I'm going to call it capital P sub I1. That's some other polynomial that doesn't depend anymore on the first block. Right, so I'm just like this capital P I1, that's my abbreviation for this sum here. And two technical things. One is it's easy to see that the influence of the I first variable, so this is one of the variables in the first block, this is actually the expected square of this polynomial p sub I1. If you take the square uniformly over the sort of the Boolean cube for these, what is it, d minus 1 times little n many variables. And similarly, the variance of the whole polynomial p is actually the sum of these influences. If you use these Fourier theoretic formulas, which I haven't told you, then these things are very easy to see, so just trust me on this. And now we know that no matter which pluses or minuses you're going to stick into the variables, this guy here is always going to be at most 1 in absolute value. Right? So on the one hand, we have an upper bound here, like every assignment that we put in of pluses and minuses for the variables, this thing is at most 1. But let's also try to prove a lower bound on the value that this polynomial can take by trying to find an assignment that makes the value of p somewhat big. And then we can combine that lower bound on the value of p with our upper bound on the value of p, and we get something. So let's try to maximize the value of the polynomial that we get, first by using random assignment of pluses and minuses to the blocks x2 up to xd, right? So this is d minus 1 times little n many variables. I'm just plugging random pluses and minuses in there for those variables, and I'm going to be slightly smarter about the settings for the first block. Right, and my goal, remember, is to sort of make this expression as large as I can be. And I just put random variables here for these variables, and let's see how big this pi1 will be with the random assignment. So there's this thing called the multivariate Kinchin inequality. It says the following: the expected value of the absolute value of this polynomial, if you stick in random pluses and minuses for its variables, is at least something like 2 to the minus d, in fact 2 to the minus d over 2, times the square root of the expected square. So this is a multivariate generalization of the Kinchin inequality, and it says that the sort of, in absolute value, this thing is not too small. It's sort of lower bounded by an exponentially small factor in d times this thing here, and this thing here is actually the influence, or rather the square root of the influence. Right, so we start to get a lower bound on values of subparts of our polynomial in terms of the influences. And now we'll make the more clever choice of how to choose the first little n bits. And what we do is, so note that, remember, our polynomial is of this form here, and these pi1s, they're sort of large-ish in absolute value. But some of them might be positive and some of them might be negative, and we want to make the sum as big as possible. So what do? We want to have the absolute value sign here, and we do that by just choosing xi1 to be the sign of pi1. Right? And then this gives you kind of an easy lower bound on what this can be in expectation. Right, so the expected value of px under this assignment of variables that I just mentioned, well, it's going to be this. You choose the xi1 variables so that you get an absolute value here. You pull in the expectation, you get this. You apply what you get from Kinchin. And now here you get square roots of influences. And we're only looking here at the influences of the little n variables in the first block. And you can divide here by the square root of the max influence in that block. And this gives you this here. And the nice thing is that here we have the sum of influences, no longer the sum of square roots of influences. And the sum of influences just is variance. And now if you rearrange, you actually get a lower bound on the max influence. You get this. So what this says is that the largest among the influences in the first block is not too small. It's polynomial in the variance, which is good. And it's exponential in the degree, which is not good. Right, so the Aronson and Byness statement would be sort of some statement like this, but then with a polynomial dependence in d rather than an exponential dependence in d. And unfortunately, you can show that you can't get such a result if you plug in pluses and minuses for your variables. So now let me just sort of tell you how to fix this failed proof attempt by using sort of much higher dimensional instantiation. So we're not going to plug in pluses and minuses anymore. We're going to plug in random large dimensional unitaries, and we're going to analyze what they do using something called free probability theory. Right, so we now want to fix the failed attempt using free probability theory. Free probability theory, think of it just as a way of sort of nicely handling random matrices. Right, so not only do we know that if we plug in pluses and minuses for the variables that the value is at most 1, but we have this property, this assumption that the completely bounded norm of p is at most 1. And that means that even if we stick in very large dimensional unitaries for our variables, for our capital N variables, we will get something whose operator norm is at most 1, no matter what kind of unitaries we stick in. Right, so now we're going to do a similar proof strategy as before, but instead of taking random pluses and minuses for the blocks x2, x3 up to xd, we're going to take random unitaries of large dimension for all of those variables. Right, so remember these are like d minus 1 times little n variables, and for each of them I'm picking a very large dimensional random unitary, let's say d by d, capital D by capital D, think of capital D as huge. And we stick that in, and we get a matrix, and we know that the operator norm of that matrix, no matter what we stuck in, is going to be at most 1. Well, sorry, I think I'm running ahead of the story here. So the thing is that large dimensional random unitaries are kind of hard to analyze, but there's this thing called free Haar unitaries, which you can think of mathematically as an abstraction of infinite dimensional unitaries. And I'll spare you the technical details there, like we sort of give an introduction to this area in the appendix of our paper. But it sort of allows you to very cleanly analyze what happens with large dimensional random unitaries. And there's two results that we use by Collins and Mail and Kemp and Speicher. So Collins and Mail showed that the operator norm of a polynomial P, where you stick in random unitaries, is sort of the same as the norm in some C star algebra corresponding to free probability if you stick in free Haar unitaries for the values, right? And here I'm really waving my hands. And then their second result is Kemp and Speicher, and they showed that if you stick in these free Haar unitaries, the norm that you get is at most polynomially related to the L2 norm of PI1, which in turn was the square root of influence. And lastly, I have to tell you how to choose the variables in the first block, which previously we chose as pluses and minuses to get absolute values. Now we need to do the analog of that for large dimensional matrices. And what we do is we take the polar decomposition of the matrix PI1 after this choice of variables, and we sort of cancel the unitary in that polar decomposition by our choice of xi1. And this then leads the PSD parts of all these matrices to very nicely add up in the same direction, in the same way that choosing pluses and minuses in the field proof from the slide before leads you to sort of add up the values in the right direction. Right, and this will give you the AA conjecture for homogeneous P of this form. So there is a variable of influence that's at least quadratic in invariance and with linear loss in the degree. And for the non-homogeneous case, you need to do a few more tricks, and you lose a d to the power 4, but it's still polynomial in d, in contrast to the previous slide, which had exponential loss in d. Right, so my summary slide, this is what we proved. We proved Aronson and Wiener's conjecture for the special case of completely bounded block-multilinear forms. If this form, so this polynomial, has low degree, then it has an influential variable, and this then in turn implies that you can efficiently simulate it almost everywhere by a classical algorithm that's not much more expensive. We used free probability theory to get a handle on sort of the operator norm of matrices that are functions of large random unitaries. But simpler proofs were subsequently found, one by Makrand Sinha and another one which I think is even simpler by Fran Escudero Gutierrez. A future work is, the first future work is obvious. We should finally prove this friggin' AA conjecture. I don't know how to do it. There's like one idea missing there, maybe two. You might remember from yesterday morning the talk by Yamakama and about his paper with Jandri giving an exponential separation without structure, so basically on the whole Boolean cube. But that does not refute AA, as he also said yesterday, because that's for a search problem. It's not for a decision problem. You can always try to show almost everywhere simulation without Aronson and Wiener's, though in a way those two things are essentially equivalent, though you don't have to use the language of influences to get the simulation. And last but not least, we can try to find more applications of free probability theory in quantum. There are some nice applications already in non-local games. That's it for me. Yep.
We'll have time for one or two quick questions.
So I'm only somewhat familiar with this area.
Yep.
You end up selecting unitaries as inputs. How does that then map back to, say, the actual input values that one might choose?
Well, this is really sort of a structural analysis of properties of the polynomial, right? So like the simulation algorithm just follows from the fact that no matter what polynomial you have, you're going to have a high influence variable, and you just query that. I'm not sure if that's answering the question.
I think that does answer my question.
Okay,
thank you.
Yep.
Other questions?
Hi, thanks for the talk. I was wondering if you could speak briefly about the last point you made on the last slide about applications of free probability to non-local games. Yeah, so like if you try to analyze sort of the best quantum strategies for Bell inequalities, for Bell inequality violations, right? You have to sort of specify operators for Alice and for Bob. And in some cases, you can get the best possible violation of your Bell inequality by sticking in large dimensional random matrices for the strategies. Yeah. Like I think there's a paper by Aram Harrow and a few others who analyze this. It's referenced in our paper if you want the reference. Yep.
Hi, Ronald. Thanks for the nice talk. I wonder if you could say a few words about the techniques that are used in the other proofs.
these proofs here.
Yes.
Yeah, so Makrand's proof is sort of similar to what we do, but it simplifies some things by just sticking in a simple Cauchy-Schwarz to replace part of our proof. While Fran's proof, in fact, he's in the room somewhere in case you want to ask him, he actually sort of puts a lower bound on the completely bounded norm of P by finding specific settings for all the input variables as relatively low dimensional unitaries. So he doesn't at all use this stuff about random large dimensional unitaries, doesn't need free probability, it's much more explicit. And I think it ends up giving the same bound. Yep.
Let's thank the speaker again.
Yep.